Okay, I'm not going to draw it in front of you, but I've constructed a series of tangent lines to the orange graph, the graph that represents y factor 5/2. And the slopes that I get, well, are represented hopefully with about the same run. I mean, here's the run, here's the run, here's the run. The runs look reasonably consistent. And we see how the rises behave. So the rise of this tangent line, the tangent line is at this point, and the x-coordinate of that tangent line would be about here. I originally drew it here, but that's not correct. Okay, it should be here. Which means that since I'm representing the x-coordinate of that point over here, the point should be here. Okay, now, right there is the rise of this triangle. Now, I've got a tangent line at this point. X-coordinate of that point is about here. And it's a little hard to see it, but I've got a red tangent line here, and then another one here, and then another one of different slope here. And if I look at the rise of this graph, you see I have a rise from here to here, and the rise here does not quite double the rise here. I would say it's about 1.7 times as great. So I'm going to represent that at a point at this x-coordinate. Let's pretend that one's gone. At this x-coordinate, I'm going to say we assume the slope has this value. Then at this x-coordinate, the slope appears to have about 1.7 times that value. Now if we double this, well, that's pretty good. We got that. Okay, that puts us about here. Okay, then if I move to this point, which is where the tangent line is, it appears that the rise is a little more than double the rise here, so that the rise of this graph would be a little more than double, so we would have something like this. Better be careful swatting flies out of my eyes while I've got these sharp points in my hand, but I think I can manage that. Okay, so here's a graph of the slope of this y factor 5/2 graph. And what I see is, even using the crude methods I did to approximate this graph, we appear to have a curve that looks like this. Now my question is this a power function curve? Okay, so power function curve. Now if it is, then doubling an x value should result in the same y factor. So if I took a point on this graph, an x-coordinate here, cut that x-coordinate in half, cut that in half, I should have consistent y factors between the y here, and the y here. You can construct that sort of a graph carefully and check out whether the slope graph generated by a power function graph does give you a power function curve. Now we saw that it's at least semi-plausible that an exponential graph, the slope of an exponential graph, the slope graph that you get by plotting slope versus point of tangency from an exponential graph, gives you an exponential graph. Now that was not by any means certain here, and there's no certainty in the shape of the graph that I got here, although this graph looks suspiciously like the y factor 3/2 graph, doesn't it? Still, is there a relationship? Is the slope graph of an exponential? Is the slope graph of a power function a power function? If the slope graph is of an exponential is exponential, does it have the same doubling displacement? And if the slope graph, well, the slope graph of a power function clearly has a different y factor, because this graph is concave up and this graph is concave down. They don't have the same shape at all. The y factor of this graph can't be the same as the y factor for this graph. That is, if you have a power function that's concave down, its y factor cannot be the same as that of a power function whose graph is concave up. And those are things you don't need to get too deeply into, just some observations. The bottom line here is, can you construct this curve? And if so, can you test whether it's a power function curve? And can you construct the exponential curve and test whether it's exponential, and if so, whether it has the same doubling displacement?